All right, welcome to worksheet number 7, optimization problems. This corresponds to book section 3.7. Let's say I want to cut 4 corners of cardboard so that I can make a box by folding it up, right? Like a packaging and stuff. How much should I cut so that I can make a box with the biggest volume from a given cardboard, right? So like you have a given material, you want to maximize the volume they can contain. So the question is like, how should I cut, right? This is an example of an optimization problem. It just means either maximize or minimize a certain quantity. Here we're going to maximize the volume. In this section, we'll use the concept of extrema, the global min and global max to solve the optimization problem. So what we're going to do is we're going to come up with the equation or function, and then some uncertain interval, and then basically we're going to find the maximum volume. So we're going to come up with a volume function, and then we're going to try to find the global max on a certain given interval, because the global max of a volume function means the highest volume, right? So what we learned in finding global max and global min, the same strategy, we're going to use it in these problems they're going to do. All right, let's look at example 1. Farmer wants to fence a coral, make two equal rectangular areas, okay? 2 equal rectangular areas, okay? He has only 600 feet of fencing material, fine. What is size? What size should it enclose so that it has the biggest area? Okay, fine. Okay, there's a lot of information happening. They're saying 2 equal rectangular area. He has fencing material, which is 600 feet. Fine. Okay, read the problem carefully and determine what type of problem is it. Here it seems like we're talking about the area of a rectangle type of question, because it says he wants to make 2 equal rectangular area. Fine. Determine what is to be optimized. Usually it's where actual question is. It says biggest area. So maximize the area. From there, I'm thinking eventually I want to come up with a function that represents area and then try to find the global max. All right, it says draw a picture if possible to find the equation of what is to be optimized. Okay, so it says the area is going to be 2 equal rectangles. So I'm going to draw 2 equal rectangles. Or at least try to attempt to draw it like here. Okay, so like this, fine. So in rectangle, there's length and the width. It says 2 equal rectangles, so I'm going to call this y. I'm going to call this x. I'm going to call this x because we have 2 equal ones. Okay, from here, I want to try to come up with the equation for the area. So area is, we know the area of the rectangle is just the base times the height, base times the height, or length times the width, however you want it. So that's 2x here because it's 2 rectangles, so x and x, that'd be 2x, and the height is going to be y. So area is 2x times y. In this type of question, I don't really like the fact there are 2, so here I'm going to make a little comment. We don't like it when we have two variables. We have x variable, we have y variables, because we're going to have to take the derivative and then set it equal to 0 to find the critical number and then try to find the global max. So like I have 2 variables, so it's going to be like, am I taking the derivative with respect to x or y? So I think it's easier for me to convert everything in terms of x or in terms of y. So we need the extra information. So I'm reading the question again. Second statement says he has only 600 feet of fencing material. So I want to see how I can incorporate that. So I'm going to kind of label everything here. So fencing material is 600 feet. So the entire thing, including the middle part. So I'm going to create another equation. 600 means is equal to this plus that plus this, and that. So there'll be 1, 2, 3, 4, 4x plus 3y. So maybe I can solve for y by itself. So I can say y is equal to 600 minus 4x over 3, right? So what I can do is I can plug it back into the original equation of the area. Then I can get area in terms of only x. 600 minus 4x over 3, like that. Which means a is equal to, I'm going to distribute it here. That's 200, 400 x minus 8 over 3x squared. So I think we're already at the next stage. It says eliminate all but one dependent variable. Okay, we did that. We kind of did that. So my equation now only have x in it. By using any constraint, we only have 600 feet of material. That was our constraint. So let me just rewrite that. A is equal to 400 x minus 8 over 3x squared. Let's look at number 5. Are there any restrictions in the variable? So like, let's think about x, because you're using x. What's the biggest, smallest value x can be? Obviously cannot be negative, so 0 will be the smallest value. But can x be as big as you want? Well, not really in this case, because our fence is 600 feet. So if x is 600, that cannot be, because this is already 1200, so that's not good. What if x is 300? But that's 300, 300, 300, 300. So that's already 600, so that's even more than 600. So for x has to be less than 600, so x has to be less than 150. So x has to be bigger than 0, or 0 is the smallest number. The largest number x can be is 150, because then 150, 150, that's 300. And then 150, 150, that's 300 on the top, so that'll be 600. So I'm going to write x is between 0 and 150. So that's going to be our domain. So what we're going to do is now, next part, it says use the calculus to find the maximum mix. Min, again, to find global max and global min, we'll check the critical number and then we'll check the endpoint. So to find global max, we'll check the critical value, critical numbers, and then we'll check the endpoints. So first we'll find the critical values and then critical numbers, and then we'll check the endpoints. So critical numbers, basically I have to find the derivative. A prime is 400 minus 8 over 3 times 2x. So I'll let that equal to 0. So 400 is equal to 16 over 3x. So x is equal to 400 times 3 over 16. If you calculate that out, we're going to get 75 feet. So that's my critical number. So I'm going to check that. And endpoints are 0 and 150. So let's check A of 75. So I'm going to plug in, so 75 is my critical number. I'm going to plug in 75 into the area to see what area I'm going to get. So 400 times 75 minus 8 over 3, 75 square. When you calculate it out, you get 15,000. So, and then if you plug in 0 into the equation, 0 and 0, that's going to be 0. When you plug in 150, again, I'm plugging 150 into x here. If you calculate it out, you also get 0. So from here, I can say this is the max, right? So let me highlight that. So that's going to be global max. That means that's going to give you the highest volume, basically. To answer the question, we should build a fence like this. So 75 here, 75 feet, 75 feet here, 75 feet, 75. How about this part? Well, that's my, so that's 150, so we use 300, so divide by that too, so 150 here, 150 here, right? So this is how I should build the fence. It'll give you 600, 150, 150, 150, 150, 150. So it'll get 600 feet, and it gives you the maximum area of that. All right, let's look at example 2. All right, here it says a boat in the ocean is 4 miles from the nearest point of the shoreline. Okay, so boat is here. This is the land shoreline. Boat is 4 miles. And 36 miles from the restaurant. So this is a restaurant. Okay, I'm gonna say this is restaurant. Fine. If a woman on the boat can walk 3 miles an hour and row 2 miles an hour. Obviously, it's a little faster for walking than rowing, I guess. At which point of the shore should she land to minimize the travel time to the boat to the restaurant? I guess she's late to the restaurant. So, like, just looking at the distance, if she just rows to the restaurant, that's the shortest distance, right? It's like, why do you have to go around? Like, can I just go straight, right? However, rowing is she can only go 2 miles an hour, so she can row kind of slow compared to her walking, right? The other strategy is just go here right away. Then she can walk faster, right? But then this is like the longest distance. So I was thinking of like one extreme case where she just rows to the restaurant, which is the shortest distance, but then she's like, that's only 2 miles an hour. Other strategy is go to the shore immediately and then walk, but that's like such a long distance, right? So the question is, where should she land so that she can minimize the travel time, right? So here I'm gonna do, maybe I can write this as X is here, right? So I'm gonna find where X needs to be so that we can minimize the travel time. So this is the distance time rate type of question. So distance time rate type of question. Again, the formula for speed or velocity is distance over time, right? So here I feel like we need to set up the equation that tells you what the time is, because it says minimize the travel time. So I'm gonna have to come up with the equation for time and then try to find the minimum, so global min of that. So maybe I can rewrite this, solve for time. So I can say time is equal to distance over speed. So I'm going to use that equation, okay? So number 2 is, what are we trying to do here to find the minimize time? Let's say it's going to be t. Okay, 3 and 4 coming up with the equation basically. So we have basically, she's going to go this way, I don't know where, and then she's going to go this way, right? So she has like 2 parts. She has the rowing part, and then she has a walking part. So let's see how much is going to take her to row over here to the point X, right? Well, it's distance over speed. I know the speed, I have to figure out the distance. Well, I see a triangle for X and the distance here, so that's going to be a Pythagorean theorem, right? So I'm going to write time. The first part of the time is basically distance. It's going to be radical 4 squared plus x squared, right? And then over speed, her speed is going to be 2. So this part is going to be the rowing part. And then plus how much time is going to take her to walk? Well, she's going to walk this much. If the entire thing is 6 miles and this is x, this is basically 6 minus x miles, right? So I'm going to write 6 minus x mile, that's the distance, over she can walk 3 miles an hour. So I'm going to put 3 there. So this second part of the equation is the walking time. So it's a little bit more involved because there are 2 portions that are slightly different. So I just put that as time it takes to row, and then this is time it takes to walk. This is x, so walking distance is not 6, it's not x, it's 6 minus x. All right, constraints, can t be, or can, here, luckily we only have one variable, just x, which is fine. Can x be anything? X is some point between, she's not going to obviously go backward, right? So there'll be like negative x. So if she goes to the shore immediately, that's when x is equal to 0. And she's obviously not going to pass the restaurant. So 6, between 0 and 6 will be the constraint. So our x is going to be between 0 and 6. So that's going to be our ending point. Next step is to find the critical number and then check the endpoint. So to find the critical number, basically I need t prime. So t prime is So this is 1/2 power, so, and there's 2 on the bottom, so it's going to be 1/2 from this 2, and then 1/2 from the radical 16 plus x squared negative 1/2 power times, using the chain rule, I need the derivative of this guy. That's going to be just 2x, and then plus the derivative of the second term is just, again, 1/3 is on the bottom. Take the derivative of 6 minus x, that's just -1. Which is here, let me go back. This 2 cancels out that, so 1 over, so I have x on the top, and then I have, this is negative power, so that's 2 radical 16 plus x squared minus 1/3. I want to set that equal to 0. To solve that, I need a common denominator between these two. So on the first term, I'm going to multiply 3, top and bottom. And the second term, I'm going to multiply 2 radical 16 plus x squared, top and bottom. 16 plus x squared. Yikes. All right, so as a result, what I get is, on the bottom, I get 6 radical 16 plus x squared. I have 3x minus 2 radical 16 plus x squared is equal to 0. That means 3x minus 2 radical 16 plus x squared is equal to 0. So 3x is equal to 2 radical 16 plus x squared. Yikes. Okay. I have a radical. How do I get rid of radical? I can square both sides. Square left hand side, square right hand side. So I get 9x squared is equal to 4, 16 plus x squared. So more space here. 9x squared is 64 plus 4x squared. Subtract 4x squared from both sides, so 5x squared is 64. So x is 64 over 5. X squared is 64 over 5, so x is equal to 8 over radical 5 plus minus. We know that x has to be between 0 and 6, so negative, I can ignore the negative part. So wow, that was a long process, but we're going to check. Basically, we needed that 4 as a critical number. So critical number is x is equal to 8 over radical 5. I also need to check the endpoints. Endpoints are x is equal to 0 and x is equal to 6. So if you plug in this number here, that's about 3.5778. Plug it here, plug it here. If you calculate that out, you're going to get about, so t of 8 over radical 5 is going to give you 2.8564. T of 0, plug in 0 into t, so plug in 0 here, plug in 0 there. You're going to get 4 hours. And then plug in t of 6. So plug in 6 here, plug in 6 there. You're going to get 3.61 hours. So let's kind of go back to, there are a lot of numbers here. T of 0, when x is equal to 0 means this value x is 0. That means she's going to come right to the shore and then walk. It'll take her 4 hours to get there. T6, so when x is 6 means she's going to go directly to the restaurant just by rowing. It's going to take her 3.61 hours. If she comes here, there was about 3.5, so radical 8 over 5, so this length is about 3.5. If she goes over here, it'll take her only 2.8564 hours. So this will be the minimum. So when looking at this, this is global min. So my final answer is she should land at 8 over radical 5. What is it, mile mark? And it'll take her only 2.8564 hours. All right, that was a lot. So we're done with that question. Example 4, I'm gonna get started on example 4 and then see if I can have you finish the whole thing. This is the box question we are talking about in the beginning. I have a cardboard. I'm gonna cut off 4 corners. So it's constructed with a 4x5 rectangular box. So 5 meters, 4 meters. That's huge. I'm gonna cut off the corner. How much does she need to cut off? So box has the largest volume. So just to kind of visualize, if you construct this, so cut this off, and so it's gonna look like this, right? So this part is gonna be like this, 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 and this. So I'm gonna call this X. So this, I'm gonna cut exactly same size all 4 corners, right? So cut this part off. So this part is gonna be like the height, right? This part is gonna be the height. So whatever you cut off, that's gonna be the height of the box. So if I wanna label this box, basically I'm gonna label X here. Let's draw like this. And then it goes like this to then like this, right? And then, so this is X. How about then this part? This part will correspond to this part, right? So this is 5. I'm cutting 2 corners off. So it's going to be 5 minus X minus X. So it's going to be 5 minus 2X. Same here. If I'm looking at this portion, this side, that's 4. I'm cutting off this part and this part. So whatever is here is going to be left over of this part, right? So this part corresponds exactly as this part. So that's 4 minus X minus X. So that'll be 4 minus 2X. So yeah, so this is my setup. And then volume of the box is basically area of the base times the height. So basically this times that. So that's my hint. And I'm going to have you finish the rest of the worksheet. For this, answer is going to be X is, this has a slightly complicated answer. 9 minus radical 21 over 6, about this is, which is about 0.736 meters. So if you cut that, your volume is going to be, maximum volume is 6.564 cubic meters. And that's it for this worksheet.